If you cut your skin, it heals. If you crack a modern bridge, it's broken forever. Or so we thought. The Romans didn't just build hard structures, they built smart structures, living structures. For 2,000 years, we thought their concrete was full of mistakes. See these white chunks? We laughed at them. We called them sloppy work, evidence that Roman workers didn't know how to mix properly. But in 2023, MIT discovered that these mistakes are actually a nanotechnology time bomb waiting to heal the building from the inside out. Welcome to the lost science of self-healing stone. Welcome to Ancient Scan. In 125 CE, Roman engineers poured the largest unreinforced concrete dome in history. Nearly 2,000 years later, it still stands. No cracks, no collapse, no reinforcement, just concrete and gravity defying time itself. Meanwhile, modern concrete bridges built in the 1960s are crumbling into rivers. Our most advanced structures barely last 50 years before engineers declare them unsafe. But look at Roman seawalls, submerged in corrosive salt water for 2 millennia, still structurally sound, still holding back the ocean. How is this possible? The answer hides in plain sight, those white chunks embedded in Roman concrete like raisins in bread. Historians called them construction errors, lazy workers who didn't mix their lime properly, the textbook said. For 2,000 years, every expert agreed, Roman concrete was great despite these flaws, not because of them. Every expert was wrong. In 2023, researchers at MIT aimed scanning electron microscopes at those white chunks. What they found rewrote material science. Those mistakes were genius. The sloppy mixing was precision engineering. In those white chunks, they're autonomous repair systems built into the concrete itself, waiting, ready to heal damage that wouldn't happen for centuries. The Romans built structures that could repair themselves. We forgot how. The traditional story goes like this. Romans discovered that volcanic ash from Pozzuoli near Naples created exceptionally strong concrete when mixed with lime. This ash, called pozzuola, contains silica and alumina that react with calcium hydroxide to create the glue that holds concrete together. So far, accurate. Here's where the story goes wrong. Textbooks insist Romans always slaked their lime carefully before mixing. Slaking means adding water slowly to quicklime, converting it to stable calcium hydroxide powder. This made sense. Unslaked quicklime is dangerous. Add water and the reaction is violent and explosive. Temperatures spike to 200 degrees C in seconds. Workers could be burned, equipment damaged, so obviously they slaked it first to make it safe, right? Wrong. In 2021, researchers re-examined the only surviving Roman engineering manual, Vitruvius's De Architectura, written in 30 BCE. His instructions mention mixing while the lime is still hot. Hot lime, not slaked lime, quicklime. For centuries, scholars dismissed this as poetic language or translation error. It wasn't poetry, it was the literal recipe. Romans practiced what MIT now calls hot mixing. They deliberately added reactive quicklime chunks directly into wet concrete. The heat from the lime-water reaction created localized high-temperature zones throughout the mixture. This wasn't incompetence, it was revolutionary materials engineering. Because here's what happens when you hot mix. First, the extreme heat accelerates the pozzolanic reaction in those zones, creating ultra-dense binding regions stronger than anything in modern concrete. Second, and this is the key, some quicklime never fully reacts. It remains as lime clasts embedded in the concrete. These aren't defects, they're time-release capsules, waiting for damage. When a crack forms in modern concrete, water seeps in, the crack widens, steel reinforcement rusts and expands, the structure fails catastrophically. But when Roman concrete cracks, something extraordinary happens. Water enters the crack and reaches a dormant lime clast. The quicklime that's been waiting centuries suddenly reacts. The water triggers delayed slaking. Calcium hydroxide forms inside the crack. Then this calcium hydroxide reacts with carbon dioxide from air. The result? New calcium carbonate crystals grow directly inside the crack, filling it from within, like biological tissue regenerating. The concrete heals itself. Roman structures survive underwater, in earthquake zones, through freeze-thaw cycles that destroy modern concrete in decades. Every crack triggers repair instead of failure. For 2,000 years, we called this sloppy workmanship. It was the most sophisticated self-healing material ever created, until we forgot the recipe. But proving this required technology Romans never imagined. In 2023, MIT researchers used 4 different analytical techniques to examine lime clasts at the molecular level. Scanning electron microscopy revealed crystalline structure. X-ray diffraction identified specific calcium compounds. Raman spectroscopy confirmed the self-healing calcium carbonate in healed cracks matched the lime-clast composition. Elemental mapping showed calcium flowing from clasts directly into cracks, like blood vessels supplying healing tissue. The evidence was conclusive. But could modern engineers actually recreate this? Could we reproduce what Romans made with fire and hammers using our advanced labs? In early 2023, the MIT team attempted what no modern engineer had tried in centuries: hot mixing. They heated quicklime to 200 degrees Celsius and added it directly to their concrete mixture. Safety protocols required heat-resistant gloves, face shields, and thermal monitoring. The mixture behaved violently at first. Steam erupted, the concrete churned and bubbled as water contacted reactive lime chunks. Temperatures spiked unpredictably. After the initial chaos calmed, they poured the hot concrete into test cylinders and waited. Standard Portland cement concrete reaches 70% strength in 7 days. The hot mixed concrete took longer initially, which worried the team. Maybe hot mixing was just dangerous without being better. But at 28 days, something remarkable appeared under the microscopes. The lime clasts had created ultra-dense zones at their boundaries. These zones were denser than anything in modern concrete. Porosity measured below 5% compared to 15 to 20% in standard concrete. Lower porosity means water can't penetrate. Less water means longer life. But the real test came next. Could it actually heal itself? The team used a diamond saw to deliberately crack their samples. They measured crack widths with precision micrometers, 0.5 millimeters exactly. Then they submerged the cracked concrete in water tanks and waited. Days became weeks. Nothing visible happened. Had it failed? On day 30, they removed the samples and examined them under microscopes. White crystalline material had grown inside every crack. X-ray diffraction confirmed it. Pure calcium carbonate. The cracks were healing. Crack widths had reduced by 80%. Water flow through the crack dropped by 95%. They repeated the experiment with different crack sizes. Small cracks of 0.3 millimeters healed completely in 21 days. Larger 0.7 millimeter cracks healed partially in 60 days. The pattern was clear. The larger the crack, the more lime clasts it intersected, the more healing material available. This explained an ancient mystery. Why do massive Roman structures like the Pantheon survive while smaller modern buildings crumble? Size matters. Larger structures contain more lime clasts, more healing capacity, more resilience. The Romans had accidentally created structures whose longevity scaled with their size. The bigger you built, the longer it lasted. Modern concrete works the opposite way. Bigger structures mean more stress points, more potential failures. Roman concrete got safer as it got larger. We got it backwards for 2,000 years. So we solved the mystery. Hot mixing creates concrete that heals itself. Ancient technique confirmed by modern science. Fascinating history, right? Except this isn't just a history lesson. It's an emergency exit for our climate crisis. Modern Portland cement requires heating limestone to 1450 degrees Celsius in massive industrial kilns. This process is responsible for 8% of global carbon dioxide emissions, more than all the airplanes on Earth combined. Roman lime production required only 900 degrees Celsius, achievable with simple wood-fired kilns. That's 550 degrees less, which translates to 40% less fuel per ton. And because Roman concrete was more durable, you needed less material over time. One Roman bridge, used once in 2,000 years, has a far smaller carbon footprint than a modern bridge rebuilt 40 times over the same period. We're not just building worse structures, we're cooking the planet to do it. In 2023, researchers at the Polytechnic University of Catalonia began testing something called Decrete. Modern concrete incorporating Roman hot mixing principles. Early results show 25% reduction in carbon emissions during production and significantly improved crack resistance. If adopted globally, Roman-inspired concrete could reduce construction industry emissions by billions of tons annually. That's equivalent to taking 200 million cars off the road, permanently. The Romans aren't just teaching us to build better, they're teaching us to survive. We spent billions repairing bridges designed to fail in 50 years. The Romans spent pennies to build temples that outlasted their own empire. We looked at their work with microscopes and thought we were smarter. We were wrong. They weren't building for the next fiscal quarter, they were building for eternity. Those white chunks weren't garbage, they were a gift to the future. A message written in stone that says true technology isn't about complexity, it's about endurance. And now that we've finally read the message, it's time to start building like we plan to stay here. Next week, we're using particles from dying stars to see inside the Great Pyramid. Cosmic rays reveal the chamber the size of a passenger jet hidden for 4,500 years. No one knew it existed until muon tomography found it. Subscribe so you don't miss it. And if this episode changed how you see ancient engineering, hit that like button. The algorithm needs to know that deep archaeological science deserves attention. Until next time, keep questioning what we think we know. The past is full of secrets hiding in plain sight.